So this talk is about exploring and experimenting with integrating TOR, an anonymous communication protocol, with validators on Ethereum blockchain. So the main problem we are looking at is that obviously when validators communicate with the network, they have their identity, they have their IP address, and they have their blocks that they are producing, right? So to what degree we can keep that information private? So the problem is that if an adversary or an attacker can actually correlate the IP address with the validator's ID, and it can pinpoint the validator's action slot, then that information could be used for some malicious purposes. So it's important to have the privacy for the validator, especially to maintain the overall security integrity of the chain. So specifically, if we have that information, like we know that knowing the location and actions of the validators, right? Then you can actually engage in validator sniping. You exactly time the validators with high stakes, and you force them to miss their blocks, or you coerce them into some other actions, and that in some way can harm the network. And this can lead to financial losses or for the validators, and it can also reduce the network security. Another important thing is that obviously miners or validators can extract some profit by properly or preferably ordering their transaction in a certain way that suits them or that provides them some profit. But if an attacker can identify the location and the IP address, it can engage in front running where they can place their transaction ahead of other transactions, and that can maximize their rewards. So this undermines the fairness in the system as well. And then obviously, if you can disrupt the validator with a distributed denial of service attack, you can also have impact on the finality of the chain as well. So we will quickly go over some of the existing network layer level approaches in ensuring the validator's privacy. Briefly, you can structure them in along these lines. On the network level side, we find there's a Dandelion, the Dandelion++, and there are onion routing protocols. At the consensus layer level, you have distributed validators, you have SSLE, and you have non-single leader election. And then there are some techniques that are actually a combination of both or operate at a different level, like Lightning Network or mixed nets and other non-TOR based anonymity networks. So if you compare these approaches, the main benefit, the main disadvantage that we see with Dandelion and Dandelion++ is that there are no guarantees on unlinkability. And there's an increased latency in the stem phase. And if you go into the onion routing TOR protocol, you see there's an overhead of the encryption. And then on the consensus layer, we have distributed validators, but there's coordination complexity, scalability issues, there's a performance overhead. And then some of the SSLE and SNSLE solutions are actually in R&D. There's no yet prototype or to really assess that. And still, it's the same challenge of complexity as the distributed validators. And further, Dandelion and Dandelion++, it seems to be an improvement over Dandelion, but still there are some larger differences. For example, it's single peer reliance for Dandelion, and the latency issues, and there's no complete unlinkability, only mitigation. Okay, there's other work done on integrating Bitcoin and TOR. And what happens is that they have suggested some possible attacks where the users could be de-linked using by exploiting message cookies. And then Bitcoin has its own anti-DOS protection mechanism which can be exploited in order to get some de-link information about the node. And so what we are proposing is, in the same context, we are proposing integrating TOR with the Ethereum network, like in our case with the Nimbus client. And we do inherit some of the TOR vulnerabilities. And some of the attacks that were applicable in the Bitcoin case, we can restrict them by not using, for example, the peer score. And also, we do not try to reach the TOR directly. We actually employ some other custom routing before we connect to the TOR node. So some of those attacks can be actually mitigated, unlike in the previous work. So what's our solution? So our solution is actually an integration of TOR with the validator nodes. So you have a validator client running on the beacon node with an execution client, and it engages in different roles. And then on the beacon node, we have a TOR switch that's enabled that actually communicates with the TOR network. And in the basic setup, the beacon node directly talks to the gossip PubSub network directly through the TOR switch. All the communication of TOR circuit happens here, and then it reaches the peer here. So you can see that this is where you use the independent TOR module, and this will actually incur the delay that we want to measure and we want to assess that how feasible it is. There's an advanced version of it where we don't directly talk to the TOR through the TOR switch, but actually we route it through some custom relaying. So this is in order to mitigate some of the possible attacks on the TOR that if you combine with the custom relaying can actually be handled. So in this scheme, the beacon nodes, they relay the message through the messaging network, such as PubSub network. Each beacon node can operate as a diffuser node. And validators, they initiate the messages through beacon node, and then they are transmitted either to the TOR switch. And in the default setting, we make sure that these connections are available before the next epoch, so that we don't have a connection establishment overhead. And it's important that these connections must last for a sufficient amount of time, so that communication can happen effectively. So this performance and this uptime for these connections, how robust those connections are, how fast those connections are in the TOR network, they are all important factors. So though this is a work in progress, but we do have results. We have a working prototype that's running, that's deployed, and we have multiple validators that are actually using TOR now. So here I've taken one of the TOR validators, TOR push validators, and it is connected with the Gorilla Predator network. And you can see that it has an effectiveness of around 90%. I mean, this is comparable to some of the top Gorilla validators, which are normal validators, not the TOR one. So this effectiveness is actually the ratio of the actual inclusion distance over the optimal inclusion distance. So how quickly an attestation can propagate and can be included in the chain. The earlier included, the better it is, and the higher the reward the validator would get, and more useful it will become to the network. So this is one way of measuring the effectiveness. So what we are trying to show here is that even after using TOR, the effectiveness still is comparable to other non-TOR validators. So latency that is added by TOR is reasonable. We have we'll show some of the stats here after this, and we see it is a good one step forward in terms of providing the location privacy, hiding the IP of the validator. So how do we measure the latency? So the total time it takes for the message to go through the TOR network and reach the end peer. Let's say in the normal case, we have time to send a message without using TOR, and then we see how many hops we have in the TOR circuit, normally 3, and then we look at the size of the message. So they all add up to the total time it takes for the message to reach the peer. Okay, so here are the real stats that are available right now, and we have been experimenting and evaluating them over a month, that how our TOR validator works with other ones. So you can see we took a certain time period and we looked at a certain number of attestations that are produced by one of the TOR validators, and there is a difference of around 466 millisecond, half a second nearly, versus TOR validator and the normal validator. And here you can see the there is a this is the average of these two values. So this is around a half a second of a delay, which we think is visible. Okay, then we extended the validators. We ran more validators on the same beacon node. For example, in this case, we ran 10 validators on the same beacon node, and we saw similar behavior. So you can add more TOR validators, and still the difference in the average values remains comparable and under a second, around half a second. Okay. So measuring latency is one of the things. We also want to look at what is the effectiveness of the of this validator. So whether the attestations are missed or not, how soon they are missed, and if they are missed, and how they compare with the rest of the non-TOR normal validators. So we looked over a month, and we figured out that for one of the TOR validators, we have some of these attestations that are missed for their particular slot. And this is not a significant miss ratio, and we can see easily that in the next slide you will see that when we compared it with the top non-TOR validators on the Gorilla network, Pareto network, our number of misses tend to be comparable with them. So this gives confidence in that yes, the network is accepting the messages that are coming from the TOR network. They are being included, the blocks are being produced, the attestations are being produced, and they get on the chain without much problems. And yes, there is latency of a half a second, but that did not affect the overall effectiveness and inclusion of these blocks and attestations. How we rank them? We rank them based on their effective balance and their income that was earned in the last 7 days or last 30 days. Okay, so when we run it through the TOR, we obviously want to see what's happening within the TOR. So you can see that here we have been monitoring the node that is using TOR to send the messages. So most of these numbers look pretty reasonable. There is not much overhead. For example, the bandwidth is pretty well in control, and the upload time is still, the upload is also within a reasonable time. Here we can see the usage of resources on the node. TOR is implemented efficiently, independently, so there is not much high resource consumption because of the TOR. And here you can see the lifetime of the circuits, TOR circuits. And what we're trying to say here is that some of the circuits at the bottom, they are created temporarily for under a 30 seconds and then they disappear. But then on the top, there are some circuits that are stable, reliable enough for days or for multiple hours, and they are more productive and more helpful in transmitting the messages without delay. So this is constantly happening on the beacon node that is using TOR-based validators. So availability of circuits is important. Availability of reliable circuits is important. If you're lucky, you get a reliable circuit, great. If you're not lucky, you will have an overhead. and you will have a problem finding the peers through the TOR. But this is the behavior that at the bottom you can see how the TOR is trying to establish circuits as quickly as possible. Okay, we quickly go over some of the security analysis, some of the problems that we see. Yes, obviously we bring TOR into the beacon node and let the validators talk to the rest of the network through TOR. Then we also inherit the TOR vulnerabilities. The attack surface of the TOR is inherited into our system. So we want to mitigate some of those aspects as well. So there is an end-to-end correlationship attack possible. The TOR does not provide protection against adversaries who can see network traffic coming from and going into the TOR network. And so there is a possibility of end-to-end correlation. Also, there's a possibility of fingerprinting attacks. When the protocols have distinctive, unique patterns, so they can be exploited as well. So the mitigation is that you try to reduce the distinctiveness of the TOR push, this message that is sent to the TOR, and you try to refresh the identity, and you don't touch the TOR directly. So if you don't touch the TOR directly, you will not get into end-to-end correlation attack. How do you not touch the TOR directly? You try to employ some custom routing before you use the guard node. And then there is denial of service attacks, distributed denial of service attacks that has a possibility, but it's a computationally expensive proposal to attack the TOR through denial of service attacks. However, if you try to attack the TOR entry node, TOR's entry node selection mechanism will eventually replace the effective guard node. So this may introduce delays in message transmission. So for real-time application, this will obviously be an issue. Okay. So addresses can actually, you can spam the network. Obviously, you can, the peers, when they are discovered, they can be exploited as well in order to link the nodes to their TOR connections. So you can implement RNN or spam protection mechanisms here. So here is an example of one of the attacks. So this is happening in the discovery process of the beacon node. You can create a modified discovery node, and that could manipulate the connections by changing the address port, and hence they can figure out the IP. So a modified beacon node can reply back with the different ports, and when it sees and then you can keep this table with itself. And when the TOR network peer that's coming from the TOR network connects on these of the ports, the modified beacon node knows that this is coming from this IP. So this attack. So this means that the discovery mechanism of the beacon node, which is trying to discover the peers, should also be shifted onto the TOR, okay, in order to reduce this attack. Okay, so what happens during the initial deployment? In the initial deployments, attackers can pinpoint TOR messages from their sources because you don't see the IPs that are present in the network when you start seeing IPs coming from a new sources. And you can also exploit peer scores as anti-DOS attack in the case of the Bitcoin. So the idea is that you can use separate network interfaces, separate machines, separate contexts, and you can adjust the peer selection mechanism to prevent exploitation of the peer scores. So great. So we come to a conclusion that the TOR adds a latency of around half a second. It's a delay, but is this something that is useful also or not? So in one sense, we want things to be faster, but on the other end, this can be also considered as a blessing in disguise, because if there is a non-deterministic latency because of TOR, then you can disrupt the timing attacks that can happen from the attackers, which are trying to correlate the timing of messages with actions on the blockchain network. And that extra time, because of the latency, could also be used to engage in creating unrelated or decoy transactions to confuse the attackers. So, so this is some of the good aspects of having latency because of TOR in the network. Great. So we have a working prototype. It's running on the Gorilla network, and we are also in the process of establishing an RFC around it. I will quickly try to run the link here. Okay, so here is the can I see? Yeah, here is it. Okay, so here is the, you can see the overall average score, and you can see we have around 10 TOR validators that are running, and if I click one of them, you can see it has an average score of 85%. It has produced one block successfully. It has missed attestations, but overall still it's around 100%. And here's the attestations. You can see nearly all of them have optimal inclusion distance. That's a good thing. This is nothing different from a normal TOR, a normal validator. So anyone seeing this validator will not, because of any aspects, can figure out that it's a TOR-based validator. So we encourage the teams to use it. So here is our a POC. This is where you are actually, it's shared on the Nimbus website, status website. There's a link to the RFCs, and here is a link for the live TOR validators. Okay, any questions? Thank you.
Hi, can you share the links of the, because we can't see them?
Oh, did you guys remove it? Oh,
yeah, the link of the repo as well as the RFC.
okay, yes.
The repo as well.
The repo, okay.
Okay. Yeah, thanks.
No? Okay. Anything else?
Any more questions? I recently came across an incentivized mixnet called NIM. You use TOR here, but I mean, do you have any thoughts about the future of mixnets and what would be like an ideal solution? And do you expect mixnets to have even more overhead in terms of latency, or like, just give us a little bit of brief about what you think of it?
Yeah, we have that this roadmap. Okay, so we are going it step by step. We first picked up an independent, working, trusted, anonymous communication protocol, TOR, and we figured out, does it really work? I mean, what's in it work and what's in it work? So our next step is we be moving from techniques that are established at the network layer, moving towards the consensus layer, okay? Which means SSLE or non single leader election. And then obviously using mixnets is part of our roadmap. But we haven't explored those techniques yet in terms of how they impact the latency. There are some works that take into account, they use those mixnets, but we have not yet assessed how well they compare with the TOR. Yeah.
Any more questions? Okay.
Thank you.